So this is ECE 561, 461. Our project was to develop a microcontroller that can analyze our footsteps as a pedometer and be able to be integrated to the cloud. My name is Matthew Anaya.
My name is Qihan Wang.
Billy August.
My name is Jabur.
And we'll show you a little bit about our project.
This is our design. Basically used an RF band for a cell phone holder and some rubber bands to hold it. We have two AA batteries to power the system, and it's powered as such. The band goes around the user's arm. For a nice ergonomic snug fit.
Okay, so this one is showing the current step and the goal steps, and also the percentage of the completions. And also we have the power saving settings that every 5 seconds without no action the screen will turn off. By pressing any buttons, the screen will come out like a phone. And the clean set, and if you're walking around, then you should have the step counting as 3 steps. So pretty much that's the functionality of it.
Our process of setting the goal and how we reach it using the pedometer. First, to increase and decrease the goal, we're using buttons S1 and S2. S2, which is 1.4 on the MSP432 board, and S1, which is 1.1. S1 decreases and S2 increases the goal. Now, initially the goal is set as 10, but as you see, we can change it by increments of 5. Right now I'm going to set it to 10, and then I'm going to go ahead and start the pedometer. Now, once I reach my goal, the buzzer should start, and in order to update the screen, we have to show the display. We're now at step 4, step 5, six, 7, 8, 10. And that was the buzzer to display that we reached our goal, which is 10 steps. Thank you very much.
The coolest thing about this project is the ability to connect our MSP432 to the cloud. We're able to interact with our device via the MQTT protocol. On Bluemix, we've used the Node-RED libraries to be able to interact with our device. On Node-RED, we have MQTT nodes that we could use to communicate to our device and receive data from our device as well. Right here, we have data coming in from the MSP about the pedometer steps that have happened recently. As you see, as a person is walking, we have information here coming in about the steps that were taken. Next, I wanted to tell you about the device status. Right here, we're able to see information about the MSP's device status. As you see, if I click on the if I turn off the device, we'll get a status that says the device is turned off. It'll tell us that we were at 11 out of 120 steps, and the percent complete we have is 0.091% of our goal. The next cool thing is I'm able to set the goal that I'd like to reach remotely. Right here, if I just inject this value, right here and show you, we will have a value of 120 set here. I could even prove to you that this is working by changing the value of 120. Let's do another one, 150. Let's say we'll deploy it. Once again, we'll inject. As long as our device is on, we can see that our value has changed. Now we're at 150. This functionality gives us the ability to interact with our device on the cloud. This should be a very great experience for the user.
So for the power optimization, we did 3 different things to lower our power use. First, we were able to change our clock frequency from 64 megahertz down to 24 megahertz with our system still working. Second, we put in the low power mode between every ADC conversion. So when the ADC conversions done, we put it into low power mode until the next ADC conversion. And then lastly, we turned off the LCD screen after 5 seconds of it being gone. So once we displayed the values or we changed the goals, we would turn off the LCD after 5 seconds. This allowed us to lower our, using the tools that CCS Debugger provides us, we were able to determine that our component uses around 54 milliamps. So using 2 AA batteries, which gives us about 1300 megaamps hours, we were able to determine that our system can run on 24 hours of battery life.
Memory and speed were some factors of our design that we wanted to improve as much as we could. For memory, we used a few techniques to try to decrease the amount of memory size that we've been using. First of all, one of our techniques is to make sure our variables that we use are as small as can be. For example, instead of using an integer value, an int, we can sometimes use a char value instead and still be able to do the same kind of processing on that data. Next, we use the optimization advisor that we'll talk about here shortly. And thirdly, we wrote our own register level code to try to decrease the code size and use, once again, register level code rather than the driver libraries. Hans will tell you a little bit about the optimizer advisor and what we did to find the median between speed and memory.
Hey, so this is the result that we ran for the optimizer advisor. So they actually run it into the 5 stage of the speed and the size trade-off analysis. And based on the advisor, the recommendation is for number 5. So number 5 means fully speed optimized, but you get a bigger compile code afterward. So we're gonna use the fit of 5 for the compile. And also for the optimization level, we do is the for 0 register capitalizations. And also for the floating point, since we only counting the steps number, so the accuracy for the floating number is not really required. So we're using relaxed instead of strict. So that will helping them save a lot of, to get speed of the system. And that's all for we done for the compiler side of the for the speed optimizations.
Thank you for taking the time to watch over our video. I hope you enjoyed it. It was a pleasure taking your class this semester, and this was a great project. We learned a lot from it, and we're very thankful.